Hello everyone, welcome. Let's do some questions on image processing. First question is state an example each of intensity transformations and spatial filtering. So when we consider intensity transformations, when you have an input image and a corresponding output image, the value of a pixel in the resultant image depends only on the corresponding input value. So if you consider this value to be 100, and if our operation is dividing by 2, the resultant value would be 50. So what you need to know here is the value of an output pixel only depends on the value of the corresponding input pixel. Such an operation is known as an intensity transformation. Spatial transformations are different. In spatial transformations, you have the output image, and if you want to compute the value of a pixel in the output image, you not only consider the corresponding value of the pixel in the input image, but also a neighborhood of that. Maybe 9 pixels considering a 3 by 3 neighborhood. So therefore, in this context, the resultant value depends on all these 9 pixels. Now, in this case, let's consider this operation is an averaging operation. So we have to consider 3 by 3 kernel because input neighborhood size is 3 by 3. So let's consider all ones and 1 over 9. I could have written 1 over 9 in all the cells. Now in this case, you keep each of these values in the kernel. For example, this one over here and this one over there and so on, so that these centers are located, and then you multiply, sum and put as a resultant value. This is the averaging operation because our kernel is all 1 over 9's kernel. So what are examples of these intensity transformations and spatial transformations? In regard to intensity transformations, for example, increase in brightness. Would be one. Then as a second one, histogram equalization. Intensity windowing. Are some of these examples. So contrast stretching, they are all examples of intensity transformations. Now spatial transformations, examples are noise filtering. So usually we use Gaussian filtering for this, for example. Is an example. Then edge detection. For example, using a Sobel kernel. Then sharpening. These are all examples of spatial filtering, median filtering, and so on. Okay, now let's go to the second question. So consider the intensity transformation given by S equals C times natural logarithm ln of R. R is the value of an input pixel. So R goes from 0 to 255. And S is the output intensity and C is a constant to be estimated. So C must be estimated so that we make the large maximum value of S also equal to 255 so that they can be represented using 8-bit numbers. So state the effect of this transformation is the first question. Actually, for this, the graph was not given in the question, but you have to think about the graph of the natural logarithm. So there is a problem from 0 to 1, so you have to ignore that. From 1 to 250, this is the growth of the natural logarithm. Actually, I have multiplied this by C also. Actually, I think C turns out to be something like some number in the 40s. So the output maximum value turns out to be 255, corresponding to 255. Okay. So what does this do? Now it takes now this is similar to the gamma correction somewhat. Takes a small range of dark pixels. Pixels from value 0 to 50, for example, are dark pixels. Toward the right, 200 and to 250 and so on. These are very bright pixels. So you take a narrow range of dark pixels and map them to a wide range of dark pixels. So the representation of dark regions in the image enhances. So the answer to this is maps a narrow range of dark pixels to a wide range of dark pixels. So as a result, dark regions are vibrantly represented. Okay. In a program, what is the usual way of applying a transformation of this nature? So once you compute this transformation, we will have this vector S. So this is a vector. So this will be in the range actually from 0 to 255. So we do not know exactly what each of those values are, but if you index S with some number like 53, the corresponding value to 53 would result. So if you take 53 for example here, so let me write the corresponding value as 160, some value will result. So what you do is you index S with the whole image. So usually these programs that operate with matrices know to output an array which has the same size, same shape as the input image. So this is the regular way of applying these transformations. Indexing the intensity transformation S with the whole image. So then next question is, a student's implementation of this transformation resulted in figure Q2b. What is the reason for this incorrectness? So you can see in this image there are dark pixels. So maybe pixels like this. And then the transformation has been applied. Now you can see the pixels are vibrantly represented. That is fine. The transformation has happened, but you can see some regions have become too bright. Some regions have become too bright, and the brightest areas in the original image have become black. So you can see there's a discontinuation of intensities. In a natural image like this, discontinuation of intensities do not happen. So here the reason must be overflowing. So student did not calculate C properly. C was not properly calculated, so that the values of S were not constrained to uh, yeah, excuse me. Then S not constrained to below 256, so resulting in overflowing. So because you see now these numbers, when they are represented using 8-bit numbers, the maximum value that can be represented is 255. So when you represent 256, actually it becomes 0, 257, 1, and so on. So that would have happened. Okay. Question number 3. Question number 3, figure Q3 shows a 6 by 8 image to be zoomed by a factor of 3. So this is to be zoomed by a factor of 3 using the nearest neighbor interpolation, and then it must be computed using the bilinear interpolation. And we are supposed to compute the value of the resulting zoomed image at 10 and 14. Obviously 10 and 14 does not exist. That pixel does not exist in the original image. So the question is talking about the pixels in the resulting image. Okay. So let's briefly sketch the resulting image. So that's a larger image. So that will have values from 0, 1, 2. Now it's scaled by factor of 3, and you should have this is a 6 by 8 image, so 17 must be the highest value here. So I should have drawn it larger, but since there is no space, I will not draw it as a large image like that. So this index must be from 0. It is the dimension is 8 in the input image, so the output image would be 24. So this must be 23. So we are supposed to compute the value at 10 and 14. Value at 10 and 14. So what we want to do is to compute the location of 10 and 14 in the original image. Location in the output image is 10 and 14. Corresponding location in the input image should be 10 divided by 3, 14 divided by 3. That means let's write this 3.33 comma 4.67. Okay, so now for nearest neighbor interpolation, so we have to locate this point in the input image. So we have to locate 3.33. So this is 3, and this one is 4, and it must be beyond that. See? So 3.33 would be, if this is 3, if this center is 3, okay, this center is 3, so this is 4, this is 5, so 3.33 I would write somewhere here. Then 4.67 is toward 5. Okay, this is our nearest neighbor. So nearest neighbor would be 3, 5. So intensity of 3, 5 would be 146. Okay, so that is the nearest neighbor computation. Now what we need to do is the bilinear one. So to do the bilinear one, we need to find the 4 neighbors that are around the location of interest. So once again, the location of interest is 3.33 and 4 point somewhere here, let's say. So these are the 4 pixels of interest around that. Oh, sorry. So the location of interest is here, so the neighbors are this, and this. So now we have to do the computation with those. So I'll draw them slightly larger than this. So 222, 146, 109 and 182. So these are the pixel centers and their values. So in this direction we need to have the ratio of these 2/3, these 1/3, because of this situation. In this direction, this would be 1/3, this would be 2/3. Okay, so that's what we are after. This location is what we are after. Okay, so now you will see the way to do this computation is to ratio on this. First, let's compute the value here and value there. So value here would be 146 it is close to 146, so multiply that by 2/3 plus 223 2 multiplied by 1/3. The corresponding value here would be 182 multiplied by 2/3 plus 109 multiplied by 1/3. So sorry, we have to do those computations now. So we have to pull up the calculator and do this. $146 multiplied by 2 divided by 3, then 146 divided by 3, okay, I will let you do this calculation because I cannot work with the computer, work with the calculator right now. So call this A, call this B. So now when you have those A and B values, to compute the value right here, the actual answer would be B times 1 over 3 plus A times 2 over 3. So this is the final answer. So you must get a value between 222, 146, 109 and 182. It cannot be lower than 109, it cannot be higher than 222, in that range. Okay, so do your own calculation. Maybe I can do that. Oh, I don't have a scientific calculator now, and calculators trouble me all the time. Sorry. Okay. The resulting image produced by binary interpolation needs to be slightly smaller than the nearest neighbor method. What is the reason for this? So what you are saying is the resulting image produced by bilinear interpolation should be slightly smaller. So that means this one, these areas cannot have values. What's the reason? Because when you take the numbers in these areas and ratio on them, they will fall outside the original image. So values, okay, sorry, corresponding pixels in the original image for bottommost and rightmost pixels in the output image fall outside the original image. Okay. Next question. Figure Q4 shows an image and intensity transformation function. Show the resulting image after applying this intensity transformation. So the image is shown and an intensity transformation. So this is that intensity transformation, and we are asked to find the values of pixels in the output image. So for this you have to sketch the output image. Now this is a 4 by 1, 2, 3, 4, 5, 6, 7, 8 image. I don't know why I have done that, such a large image. To sketch that. Bad idea. Okay, these are the locations you need to find. First, let's take this value 11. So when the input intensity is 11, somewhere here output intensity is 0. When the input intensity is 24, output intensity is 0. So 24 is here. You see the output, this maps the input intensity to the output intensity. So let's take 120 for example. If the input intensity is 120, output intensity would be 120. So if the input intensity is 160, output intensity would be 255. So actually we can find the equation of this line. So it is 80 is this point, and this point is 160 255. So you can find the equation of the line y equals mx plus c. So you can find the gradient and you can find the c, but I will do it graphically. Hopefully I can do it graphically. Then 48 is also here, it's 0. 65 falls below 80, it's 0. 28 below 0, 0. 80, at 80 it's 0. At 143, now you have to calculate. I think let's do the full calculation. Okay, so m is 255 minus 0 divided by 160 minus 80. So this one is equal to basic calculations. 255 divided by 80, 3.1875. So what is C? Substitute this value of 0 was an 80. 0 equals m times x is 80 plus C. So C can be found as times 80 minus 255, I think. Yeah. So the equation would be y equals 3.1875x minus 255. So you substitute 143 in here. And for 143 you get 200. So here you get 200. So I think you get the point. So for many of these you will get 0, but for some you will get large values. But for values beyond 160, is there any value beyond 160? For 161, for example, you will have 255. Okay, so I think you can fill all the other numbers. So you have to do individual calculations like this because you already know the m and the c. Then just a matter of substituting. I think your calculators can do that. Okay, question number 5. Figure Q5 shows 3 4x5 images. Oh, they are not 4x5 images. 4x3 images. 3 images of intensities in 0 to 7. So intensities are usually from 0 to 255. In this case, I have chosen 0 to 7 for convenience. Compute the histogram of the 3 images. Okay, so the histograms are very easy to compute. 0, 1, 2, 3, 4, 5, 7. These are the intensities. So you have to mark the values of those. So here this one has 7, 7, 7, 7, 7. That is 5. So you just have to count the number of pixels with that value. With 6 circles, 6, 6, 6, 6, 6, 4. So 7, 5, 6, 4, and with 5, 1, 2, with 3, 1. Okay, for this one, is for this one, 0, 1, 2, 3, 4, 5, 6, 7. With 7, 1, 2, 3, 4, 5, 6, 7, 8. A little bit higher than the previous one, 8. Then 6, 1, 2. Then 5, 1, 4, 1. Okay, this one. For this one, 0, 1, 2, 3, 4, 5, 6, 7. With 7, 1, 2, 3, 4, 5. 6, 1, 2, 3. Then with 5s, 1, 2, 3. 1, 4. Those are the histograms. Then identify the similar pair of images. So similar pair of images obviously has to be identified by similarity between histograms. So you can subtract the histograms and get the absolute values. So let's call this H1, H2, H3. So distance between H1 and H2 would be at 3 there is a 1 here, 1 minus 0. Let's take the absolute values. You can use the Euclidean distance, square them and get the square root. That is too much trouble. Square them, add them and get the square root. So we get absolute value. At 4 there's a 1, there's 1 here. So at 4, 0 minus 1. Okay, a bit more clear here. So this one, and at 3 nothing. This one is that. This nothing is this. See, at 4 here there is nothing, that is this one. At 4 there is a 1 here, that's this one. Oops. This one. Okay, then at 5 there's a 2 here. I write all the values which are there, otherwise you don't have to write. If both are 0, distance is 0. Plus at 6 you have 4 and 2. At 7 you have 5 and 8. So 1 plus 1 plus 1 plus 2 plus 3. So you will have 1, 2, 3, 4, 5, 8. Distance between histogram 1 and 2. Then let's find the distance between histogram H1 and H3. So directly I'll write the answers. For 0, 0. For 1, difference is 0. For 2, difference is 1. For 3, difference is 1. Oh, sorry, 2, difference is 0. For 3, the difference here, this is 1 in the histogram 1. In histogram 2, for 3 there is value is 0. For histogram 1, value is 1. Let me write it, 1 minus 0 plus. For 4, both both are 0. For 5, 2 minus 3. For 6, 4 minus 3. For 7, 5 minus 5. So you will have 1 plus 1 plus 1 is 3. So that's quite close. Then finally you need to get the distance between H2 and H3. Can we quickly write it? At 4, 1. Here nothing at 4. Nothing. 4 is 1. So that's 0. At 5. This one has 2. This one has 3. 1. At 6. First one has 4. No, 2 and 3. I'm doing 2 and 3. At 4, 0. At 5, 1. At 5. At 6, 2 minus 3. Am I doing it right? Yeah. At 7, 8 minus 5. This is 2 plus 1 plus 3. This is 6. So you can see ASEAN's image 1 and 3 are the similar ones. So when you just look at them also, you can see they are sort of similar. Okay, let's do the other questions in a different video. Thank you.